Okay, so let's start. So I got some feedback from my TAs about the exam today. So who did the exam today? And what's the general consensus? Easy, difficult, hard, too much, too little, insufficient, bad? What's the long, difficult, okay. Yeah, okay. Yeah, we appreciate the feedback. We talk about this. Every time a quiz or an exam, I'll talk with the TAs and I get a response like, what's going on? Okay. Okay, now that's useful. So we'll make it really easy then for Wednesday, yeah? No. It needs to be fair. So anyway, so one thing, by the way, that you might wonder, so I'll just be clear about this. People sometimes say, you know what, it's much better to be in the Friday lab session because then you know everything that's being asked that week. It's much easier, yeah? That's what they always say. It's in other words, it's a disadvantage to be in the Monday session. Now, so this is the third year I'm giving this course, and if you look at the statistics of the individual sessions, they're virtually similar. So it's not that the Monday session does worse than the Friday or Wednesday session. Okay? So in other words, so you know, there is no statistical difference in mean and standard deviation between Monday and Friday. I don't know if this makes you feel better, but so you know. And again, there's little we can do about this because we don't schedule this class. Ideally, we have one lab session with 200 students with 5 TAs for the few hours, but that's not possible. Because there's no room that can hold all of you. So that's why. Okay, so today we'll talk about chapter 9, pages 455 to page 480. So 455 to 480. And chapter 9 is about least squares. And you might have heard about this somewhere in the past. So the summary is that in this lecture and the coming two lectures, we will learn how to solve least squares fitting problems. So remember, on Friday and Wednesday, we had some data points and we defined a certain model with unknown coefficients and we wanted to fit those coefficients against the data. What we're doing in this chapter is virtually identical, but it's a little bit broader. But everything you learned in chapter 8, you can apply to chapter 9. So this Gaussian elimination approach, the backslash operator, you can also apply to chapter 9. So chapter 8 and chapter 9 are very closely related. So if you understand chapter 8, you likely will also understand and maybe even appreciate the material of chapter 9. So what will we learn is we will learn how to solve least squares problems, inversion problems, or estimation problems. Now, we'll talk again about the residual factor. By now you know what the residual is, but we'll talk about it again. We'll talk about the R2 statistic, and because you can imagine that if a model fits the data, that you like to quantify how well your model or data, how well your fit actually, the closeness between the data and your model, you like to quantify that closeness, okay? Because one person might look at the data fit and say it's really good, where someone else might say it's really bad. So we need quantitative measures, and the R-statistic, the R2 statistic, is one of those measures that quantifies how close your model is to the data. Okay, so if your system of equations is consistent, remember, then you have no residual. So that means the rank of A and the rank of A and B jointly, they're equal. So B is like linearly dependent on A. So we have no residual, and then the R2 statistic will be 1. 1 is maximum value. 1 means perfect fit. If your system of equations is inconsistent, then the R2 statistic will be lower than 1. And the R2 statistic ranges between -infinity and 1. And the lower values are not preferred. Now, also, hopefully, we have enough time today there's an example in the book, and we'll go over it in class, that shows that, hey, we have a nonlinear function that appears nonlinear that we cannot somehow solve. And there is approaches that you can linearize a function that's nonlinear so that you can still apply Gaussian elimination. And that's by using a transformation. Okay, so these are the 4 things we'll talk about today. That's the goal. Now, so the central theme of this chapter is that we have collected some data and we like to fit a model to this data. Okay, so you went to the lab or you went outside and you measured temperature versus pressure, or you measured A versus B. Then you get a number of data points and now you like to fit a model through that data. Now, least squares can help you with that. Okay, so we can skip all this. So let's just start with a simple example. Okay, so again, we always clear the screen. Yeah, clear. Clear all CLC. So now I am, you see I'm on top. I forgot everything I did this weekend, which is always useful. Load XY. So the first thing I do is I load a MATLAB binary file with XY data. So what is in here? I can see that with whos, yeah? And I see that I have X and I have Y. So I have some X values and I have corresponding Y values. So I have 10 X values, it's a horizontal vector, and I have a horizontal Y vector, the corresponding Y values. Now I have no idea. When I look at this, I'm a little lost. So what do? We actually plot this thing, okay? And we add some labels. So, and I also add a nice title. So what did I do here? I went to the Anteater pub and I measured the temperature, I think, yeah? So 1 degree Celsius, that's pretty low, yeah? Anteater, I don't know, what time does it open? The Anteater pub, 9 o'clock, 10 o'clock? No one knows, okay. Everyone is under 21 years old. So yeah, 1 degree Celsius in Irvine is 34. Nah, then it needs to open at like 3 a.m. or so in the morning in the winter time, because 1 degree Celsius here in Irvine is really low. But anyway, I did come up with this data. So what I measured is I measured the temperature, and at the same time I measured the number of drinks so everyone coming out of the bar, I asked them, how many drinks did you take? And I explicitly told them there cannot be alcohol in those drinks, yeah? You know me. Yeah, I never talk about that. So that's why it's non-alcoholic, yeah? If there's people above 21, you can remove the non. Yeah? So this is what I got. This is the data that I got, okay? So now I look at this data and I'm like, you know what? I like to fit a function through this data so that I can predict how much drinks I would get if the temperature, for instance, is 12 degrees. Or if it's 7.5 degrees, like in between measurement data. So we fit the model through this data. And we can use least squares for that. Now, so imagine that we fit a linear model. This is my model. That is Y is the number of non-alcoholic drinks. Yeah. Is C1 times X, X is the temperature, yeah, plus C2 times 1. And I put that 1 in there so that we build our matrix A, that it's clear that there's a 1 there, yeah? So I have my data. Oh, I don't know, let's see. I guess he's lost. So we have the data, and now we fit the linear function through this data, yeah? So what we have is this simple model. The number of non-alcoholic drinks is an unknown parameter times temperature plus another unknown parameter. So C1 is also called the slope, and C2 is also called the intercept. Now, based on chapter 8, we now know we can solve this problem by solving a system of linear equations with the backslash operator. So the first thing that we do is we set up the matrix A. Now, if you work this out, then what we have is that the first column of A is X, and the second column of A is 1, And that's what you see here. So if I look A, yeah, so this is my X. So if I multiply this with C1 and C2, I have C1 times X plus C2. And that's why I added this 1 here for clarification. And that's what you see here in the second column, yeah, here. That's the C2 and this is X, X times C1. So, okay, so now I have this. Now B, we know that B are the measured Y values. Now we know that Y is in this case horizontal and B needs to be vertical. So we transpose the Y values. That's Y prime. Okay? Now I have everything. So now I can use Gaussian elimination with the backslash operator. So multiply at the left-hand side of B with the inverse of A. Okay? And in this case, A... Why do we need to do it this way? Because remember, if we do the size of A is 10 by 2. And this is not a square matrix. So I cannot use the inverse. Gives an error, yeah? Inverse A matrix must be square. So we always use this equation, always works. So now what I have the slope and the intercept. Okay? Now, so my slope, do these values make sense? Now, you see that the number of non-alcoholic drinks increases with temperature. So there's a positive relationship between the two, yeah? If the temperature increases, the number of drinks increases. So it makes sense that my slope is positive, which means there's a positive relationship between temperature and drinks. Intercept is that place where we cross the y-axis at x is 0. Now what you see is that it makes sense more or less because 5 is in this vicinity, so it pretty much it looks okay. So these are my coefficients. Now I have my coefficients, I can predict my model, I have my original x values, I multiply them with the first coefficient, the slope, and I add the intercept. So basically what I now did is I calculated my predicted values with my model. Now I know the coefficients and I can plot this, of course, and I can add a nice legend. So this is what I get. So what do we see here? Is this solution consistent? It's very spontaneous. Yes or no? 50% chance. No. So you see a residual, yeah? Now, I don't spend time on that in this script, but we know how to figure that out prior to fitting, and that is that we can compute the rank of A and we compute the rank of A and B. And what you see that B is linearly independent of A, and that proves our point. This is inconsistent. So in other words, based on the information in A, we cannot perfectly predict B. And that's what you see here, that the rank increases. So, but you also see it in this result. You see there's a residual. Now, we can calculate that residual. This is our residual, is the predicted value by our model or function minus the measured value. So residual is now a vector, an horizontal vector with values. So in the first case, you see that our model predicts a larger value than our actual data point. Now, what you see here is that the residual is positive. Model minus actual data. So our model overpredicts the data. In this case, what you see is that our model slightly underpredicts the data, and that's the residual is negative. So now we have what we call a time series or a series of residuals. Okay? Now the question is, when you're writing a paper or so, you like to quantify how well your model fits the data. Is this a good model? Imagine that I come up with two different models, I both derive the coefficients, and I both get a data fit. Now I like to determine which model is better. So what is really useful are statistics, diagnostics, that somehow summarize the residuals in a single number, so that I can compare that single number between two different models, for instance, and then can say, you know what, that model is preferred because my diagnostic that summarizes the residuals is better, higher or lower, whatever is preferred. So, and if you like, we can show the residuals here. We open another figure. So this is how the residuals look like. Again, this is the temperature. This is the residual. And what you see is that it's not zero, so that it's inconsistent. Yeah? Now, how can we summarize the residuals? Now, the book comes up with a statistic, which is the R2 statistic. Okay, and what it comes up with, this is the formulation of the R2 statistic. And the R2 statistic is formulated as 1 minus the ratio between the L2 norm of the residuals divided by the L2 norm of the measured values minus the mean of the measured values, and then we square that whole thing. So that's the R2, and you should know this, okay? There's very few things I ask you to know, like equation-wise, but these ones will come back in your quiz, quiz 3. So this is what we call the R2 statistic. So I can compute this statistic, and what you see, it's 0.9948. 1 is perfect. If I had an R2 of 1, means that I perfectly went through the data. So this is pretty close to perfection. And that makes sense because our model fit looks pretty okay. If you look at our model fit here, you see, it looks like we did get it right. There were just some places that we were a little off. But overall, we did get the pattern, the trend, we got it perfectly right. So this R2 statistic ranges between 1 and minus infinity. 1 is perfect. Minus infinity means really, 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 really bad. And why? Look at the formulation here. We have this thing, the L2 norm of the residuals. In other words, if the residuals become really large, then the L2 norm, then this value becomes really large. Then we divide it by some constant because y and the mean of y are known. They are independent of the model fit, so this part is known. So if this gets really bad, then this number becomes really large. Then you square that, becomes really large, and you get 1 minus a really large number. So the lower the L2 norm of the residuals, generally the higher the R2 value. Okay? Now this equation that you have over here, you can write it out, of course. This is similar to this equation because A over B squared is identical to A squared over B squared. So the norm of residual squared is the sum of squared error. And there we go back to, so this is similar, so we can calculate it here for those who don't believe it. So you see you get the same result. Again, if we go to the top one, we have something over something squared. That's the same as something squared over something else squared. Yeah? You can write it out mathematically. But the good thing is that the norm, the L2 norm of the residual squared is also what people call the sum of squared error. You might have heard of that before. Now here, the R2 statistic ranges between minus infinity and 1. And again, that R2 statistic can be used to compare the fit of different models. So that you know which model is preferred. Which model best fits the data. Another statistic that's often used is what they call the root mean square error of the model. In the case that we have a consistent solution, that means the RMSE is 0. The R2 statistic is 1. Now the root mean square error is the average distance from the model to the data. So that is the residual squared. You take the sum, so that's a sum of squared error divided by the number of residuals, and you take the square root from that. Okay? Not so important. Okay. Now, so what we've done so far is we've solved this problem in chapter 9. This problem, using the same things we've done in chapter 8. Okay, so we did exactly what we've done, what we've learned in chapter 8. We applied it to chapter 9. Wonderful, yeah? You know one method and you can apply it to a lot of different problems. This book goes a little further though, and at one point it starts talking about the least square solution. And that's what I call here solution 2. So I can solve the same problem as we just solved, but then a different approach. The least squares estimate. Okay, now, and there's an equation for that, and that's on page 459 to 463 of the book. The author derives the solution, but essentially what you end up with is this, okay, where it says A prime times A is our original A matrix, times C is equal to A prime times Y, and now we need to solve for C. And we know how to do that by now. This here is equal to this. Yeah, remember we need to move the left hand side, A prime times A, to the right hand side. The way to do that is we need to divide the right hand side by A prime times A. So somehow we need to use the inverse of A prime times A. And this is the way you do it where the backslash operator comes in. It's the same. So, I had my original solution with the Gaussian elimination, and I can do the same thing with least squares, and I just type out that the solution here, A prime times A divided by, or the inverse of that, times A prime times Y prime. And why is it Y prime? Be careful here, because Y is horizontal. If Y wasn't horizontal but vertical, you could have just removed this, okay? The only reason I have a prime here, transpose, is because my Y values are horizontal, okay? But you see, my C least squares and my C Gaussian elimination are identical. So I want you to know the least square solution, but what you will see, it's the same as the solution that we got from Gaussian elimination in chapter 8. So what we've done so far is similar to what we've already done in chapter 8, with the general difference that in chapter 8 we had, for instance, 4 coefficients and we had 4 equations or 4 data pairs. Here, now we have 10 data pairs, yeah, x versus y, and we only have 2 coefficients. So we have more data than coefficients. But for the solution it doesn't matter. So you see that the Gaussian elimination and the least squares, they're identical. Now, in this case, what you see is we fitted a linear model through our data. And you might know this from high school, but if you use a linear model, you have a direct solution for the slope and the intercept. And so we use Gaussian elimination and least squares, but you actually have a direct solution for both these 2 coefficients. So, and that's in the book. You don't have to know this, but if you apply that solution where x and y appear, you see that my C1 direct means that's the direct solution is 1.9654. That was our slope. Now that's the same as what we just got, and this is the intercept. And these results are identical to what we got from Gaussian elimination and least squares. Okay? Now then the book has a function that's called linefit.m. Okay? And this function that's a function that the author wrote. It's called linefit. So if you have some x and y data, okay, then this function will fit a linear function through that data. It will return C. You see, it will return the coefficient, so the slope and the intercept. It will return the R2 statistic. And so these are the output arguments. This is the function name. So you see it's called linefit.m, and that's why it's linefit. This is input argument 1, input argument 2. So we can execute this function if you like, and we'll basically, what we just did, that's what's going on. So here, you see, we get the same results. It's just now a function. So now with any combination of x and y, I can run this function, and I will get the best function fit, linear function fit, through my x and y data. So x is a vector, and y is a vector. And you see in here the synopsis, and it tells you exactly what is what. Okay? Now, then of course we can check what's now the difference between the line function and the least squares, and you see that the difference in coefficients is 0. So, in other words, linear model, we had a linear model, there's 3 solutions. That is Gaussian elimination, always applies. That is least squares, always applies. And in this case, in line fit, because it's a linear model, you can mathematically derive the optimum coefficients. You don't have to iterate really. You don't have to set up a matrix A and B. You can just derive it with a closed form expression. And those closed form expressions are given over here in the book. So you have a direct estimate of the slope and the intercept. So the slope is line 172, intercept line 174. Now, let's consider another example, okay? Let's look at this. So, same procedure, but now we have another example. So we'll clear all, clear all CLC. So we have new XY data, and let me remove this. I'll remove that, and I just plot this data here. So you see, this is the data we have. Now, you cannot really consider this to be linear, yeah? I mean, I can fit the linear function maybe through this part over here, like there, this part, but I'll miss out on that part. So I need some parabolic function or so. I need something that goes like this. So anyway, this is my data. So, nice. So who composed that? Is that a famous composer, or is that composed after many drinks or so? Okay. So now, someone saw that data and said, you know what, I look at that data and this is what I think we should fit. This is the function y, so those are the y values, yeah, is equal to 1 over x times C1. So C1 is an unknown coefficient, plus C2 times x. So someone looked at that data for hours and concluded this must be the function that fits that data. So y is 1 over x times C1 plus another coefficient times x. So this has 2 unknown coefficients. Y are my y values, x are my x values. So I know my x values, I know the corresponding y values. So, now yeah, we can solve this problem. We have 9 combinations of x and y, and we only have 2 unknowns. So this is an overdetermined problem. Now we set up our A matrix, and we know by now that the first column must be that what's in front of C1, that's 1 over x, and the second column must be what's in front of x. So that, or what's in front of C2, so that's x. So what I did here is A, I set up this matrix A, and what you know is that x is horizontal, yeah? And A should be vertical, and that's what you see here, the transpose. Okay? So that I get nicely 2 columns. And you can go to your matrix algebra, matrix times vector algebra. So it gives me this. This is the first column is 1 over x, which pertains to 1 over x times C1 plus x times C2. So C1 and C2 are the coefficients. So this is 1 over x and this is x. Okay, and that makes sense. The largest x value is around 4, and that's what you see here. that the largest x value is around 4, and then we have one or close to 4. Now yeah, these are the different x values here in the second column. So we have A. Now A is typically the hardest part. Now we know that B are simply our measured y values. Now B again is horizontal, and we know that B needs to be vertical. So now I have A and B. So B are my corresponding y values here, yeah? Just the y values. Now, so now I have A and B, and now I know, I've learned last chapter that I can derive my coefficients by doing A backslash B. So what I get is, these are my coefficients. So apparently, the best fit to this data is y is 1 over x times 4.26 plus 1.31 or 1.3 times x. That's my script. Now, another solution is we can apply the least square solution. We know that by now. That's a prime times a backslash a prime times y prime. And y prime was equal to b, yeah? Because we said here that b is y prime, okay? So we can do the least square solution, and what you'll see is you get the same answer again. So it doesn't really matter, but this is called least squares. Now let's now plot our function fit. So first create some x values between the minimum and maximum x value that we measured, and then in 100 different values. And now I simply predict the y values. Remember, the function was c1 times c1 divided by x, or it was 1 over x times c1, which is equal to c1 divided by x plus c2 times x. Now, so now I have my x values that I like to plot with corresponding y values. That's why I call x underscore figure. So now, this is the fit. And I can add a legend. And you see, this is how it looks. So is this a consistent solution? No, it's not. You see that it doesn't go perfectly through the data. So this is the best attainable fit. This model has only 2 parameters, and unfortunately we cannot perfectly go through all the data points. And that's fine, because oftentimes data contains errors, measurement errors. So you typically never want to go perfectly through the data, because data, you know, in this case, I don't know what this is, but this could be subject to a significant measurement error, measurement uncertainty. So this fit looks pretty good. Now we can calculate the residual, and this is my residual here. You see that the residual is there. So we had nine data pairs, and this is the y residual, model minus data, or data minus model, depends on how you define it, doesn't really matter. Okay, so just to show you, we can again do this, rank A and rank AB, and you see, again, this reveals that this is inconsistent. Because B is linearly independent of A. And that's why you see that it doesn't perfectly go through the data. Okay, so we do have a residual. And now when you go to a party and you talk to your fellow friends that are working on the same problem, and instead of you bringing your figure to show everyone, hey, look how nice my model fits the data, you can just say, you know, my R2 statistic, I have found a model with an R2 statistic that is, and you calculate the R2 statistic here. You can just calculate it here, and apparently it's 0.9863. So instead of having to show this plot, you can actually quantify how well this model, this function in black fits the data using that R2 statistic. And that's why we use statistics like that, that we somehow summarize that residual factor, that in this case has 9 values, because we have 9 data points, you summarize that in a single number. And now, if I fit another model to this data, I can simply compare the R2 statistics. And then I know which of the two models, which of the two fits is the best. That's the idea of those statistics. And in most scientific publications, in top journals, people use statistics like this all the time. Okay? When you talk about forecasting, like let's say traffic forecasting, like for instance you build a traffic model that forecasts when there will be a traffic jam in Irvine. So based on the information you have now, you have to forecast at what time the traffic jam starts around Irvine area, okay? So you build a model and your prediction for today is 5 o'clock and 16 minutes, okay? So then someone else builds a model, then the actual data comes in, because at the end of the day we know what time the traffic jam was. Then you do that for a number of days, and that's what's useful to have these statistics, that you can compare one model with the other and say this model is better because the R2 statistic is closer to 1. If your model perfectly goes through all the data, yeah, the R2 statistic is 1. So if your system of equations is consistent, then the R2 statistic will be 1. And why? Now look here. If my model goes perfectly through the data, my residual is 0. So the L2 norm of 0 is? Yes. So what we have here is we have 1 minus 0 divided by something. It doesn't matter what we divided. 0 divided by something is 0. And square that, that's 0 as well. So what we have is R2 is 1 minus 0. So R2 is 1. So the closer your model to the data, the higher the R2 statistic. But this is not the entire story, okay? Okay, so last thing for today is, imagine, you see here that, you see here that the data fit is fine. I would be very happy with this in a publication or so, yeah? I usually have fits that are really bad. And they always blame it on the data, yeah? That's the way it goes. But this model has two coefficients, C1 and C2, which we derive from Gaussian elimination, least squares. Two approaches give you the same result, but you should know both, yeah? On an exam you only need to do one. We only care about the final answer, you know how to solve it. But this model, this function, has two coefficients, because it was y is 1 over x times C1 plus C2 times x. So based on this, I calculated the R2 statistic here, and that was 0.9863. Now someone else says, Jasper, you're a little crazy, you use two parameters. Based on this data, I would use 4 coefficients. Yeah, you could use a more complex model with not 2 coefficients, but 4. Now, so you use more degrees of freedom, so you have more coefficients. If you use more coefficients, you would assume that you have more flexibility so that you better fit the data. Yes or no? Does that make sense? That's really quiet. So a model with 2 parameters or 2 coefficients compared to a model with 4 coefficients. Compare it when you have a person with an IQ of 120 and you have one with an IQ of 180. Which person do you expect? We're not talking about emotional intelligence, okay? We're just talking about problem solving skills. Mathematical problem solving skills. Which of the two do you expect to do better? The one that has a higher IQ. Now that's the same with models. In this case, the black line is based on a function with only 2 parameters. But I can, based on this data, develop an alternative function with 4 coefficients. A C1, C2, I add C3 and C4. If I add more of those coefficients, I am more flexible fitting the data. So then I fit the data with a different model with more coefficients. I calculate the R2 statistic, and what you will see is that it will have increased. Because of those additional coefficients, I have more flexibility so that I might be able to better fit some of these things that now deviate off the line. So in other words, if I add more coefficients, my R2 statistic will likely go up. And people say that's not fair. Because that's what you implicitly assume. That if you use a more complex model, that your predictions, that your fit will get better. And that's where the adjusted R2 statistic comes in. Where people said, you know what, somehow we need to adjust our R2 statistic for the number of coefficients that you're using. Now, and that's what we do over here. So the standard R statistic does not appropriately consider how many parameters are being estimated and how many data points are available for this. So the number of data points minus the number of parameters or coefficients, like C1, C2, those, is also called the number of degrees of freedom. Now, if you work that out, then the adjusted R statistic explicitly contains the degrees of freedom. And that is 1 minus, this is still the same, this part, but we multiply that with something else that says that is m minus 1. M is the number of data points. So in this case m minus 1 is 8 because we had 9 data points. 9 minus 1 is 8 divided by m, 9, minus n, and n is the number of coefficients in your model. Minus 1. So you can imagine, for instance, in the really weird case where I say, you know what, I fit this data with 9 coefficients. Yeah? My first coefficient is simply my first measurement. So my first coefficient is 5.75. My second coefficient is 4.82. My third coefficient is this y value. My fourth coefficient is that y value. My fifth coefficient is that one. My sixth is... So if you use more coefficients, you can better fit the data. And that's why we look at the degrees of freedom. So m minus n is the number of data points minus the number of coefficients. And we penalize models that have a lot of coefficients. So we can look at the... So in our case, we had 2 parameters, C1 and C2, 2 coefficients, and we had 9 data points because x and y had 9 values. Now, if we call the adjusted R statistic, it's now 0.9817. So it went down a little bit, it's still very high, but the R2 statistic, the adjusted R2 statistic is very useful to compare 2 different functions with a different number of coefficients. It's the same as you have a soccer team with 11 players and you play against a soccer team with 5 players. Everyone expects you to win. So somehow you have to take into consideration in your evaluation that that other team only played with 5 people. And so that's the same here. That's why we look at what we call the degrees of freedom is number of data points minus the number of parameters. And this is called the adjusted R statistic. And sometimes what you see is that the normal R statistic, R2, is very high. But as soon as we adjust for the number of coefficients, it's much lower. Okay, for instance, imagine that I would have fitted this data with 8 coefficients. You see how bad it already is? If I would have taken a model, yeah, if I would have fitted, if my black line was the fit of a function with 8 coefficients, yeah, then my R2, my R2 statistic would have been really great. But if I would have thought, you know what, I had 8 coefficients and I fill that in the adjusted R statistic here, what you see, you get minus infinity, which means that's really, really bad. Because you could have done much better, because you use 8 coefficients. If we do 7, now it becomes pretty, and then 6, I don't know, 5, 5. So you see it's pretty good now. It's all 1. Oh wait, it's to the power 28. Yeah, I was supposed to do that. So here, oh, what am I? Here, is there another one here? We'll do the following. So let's change this to 9. So 7. So this 6, it gets higher. 5 gets higher. So the same data fit with lesser coefficients is more and more difficult. 2, and now we're back to our... If I would have had the same fit with 1 coefficient, I would have had a higher R2, and 1 is perfect, yeah? Okay, so we will continue. We still have 2 minutes, but we will continue on Wednesday with linearization, where we have a model that apparently looks non-linear. Like look at this one here, okay? You can think about it ahead of time. Look at this function. And now you have to derive C1 and C2 based on combinations of x and y. So when you look at this, you're like, how do I get the C2 out of this exponent? How do I isolate C2? Now there's tricks. If you do a log transformation on both sides, then you get a different formulation and you get something like this. And this we're familiar with. If you do a log transformation, now you have C2 and C1 isolated. There's no longer an exponent around the C2. And that's what we call linearization. Okay, so good luck. If you have any questions, comments or so, let us know. And I'll see you on Wednesday, yeah?